So good morning, everyone. I'm Noam Demri. I'm a second-year PhD student, and today I'm very pleased to present to you my work on remote magnetic alignment of spheroids in a 3D matrix to create a muscle on chip, and more generally, my work on magnetic muscle tissue engineering, which was directed by Claire Wilhelm and Stéphanie Descroix within the Kerr Institute. So, being able to recapitulate in vitro the in vivo tissue organization is one of the main challenges of tissue engineering, and it could lead to many biomedical applications, such as organ and tissue biogenesis, which in turn would lead to the development of new types of grafts, and would also allow us to test biodevices and drugs on these living tissue models instead of on animals or human patients. And it could even unlock new possibilities for personalized medicine. And in my case, the tissue that I am trying to recapitulate is skeletal muscle tissue, which represents 30 to 40% of the body mass and is also responsible for voluntary movement, which makes it very interesting for all of these applications. And in my case, I'm trying to recapitulate skeletal muscle tissue by combining microfluidics and microfabrication techniques with magnetic tissue engineering using magnetic nanoparticles. But before trying to recapitulate skeletal muscle tissue, we first need to understand its in vivo architecture. So, skeletal muscle tissue is a very anisotropic tissue. It's composed of giant multinucleated cells called myofibers or muscle fibers that are elongated and aligned in the same direction, the direction of contraction of the muscle. And each muscle fiber is actually the result of the fusion of several muscle precursor cells. And so, to recreate muscle fibers, it's necessary to force these muscle precursor cells to align and form chains that will compact and fuse together to form these fibers. And there have been many methods to do so. First of all, in 2D, you can take advantage of the substrate's anisotropy. For example, you can pattern the substrate to have an anisotropic pattern, which will force the cells to orient in the direction of the pattern. You can also add a mesh or nanofibers on your substrate with a specific orientation, which will also orient the cells. And finally, you can also take advantage of the substrate's topography. For example, in this study, they used decellularized grass as an anisotropic substrate to grow and align muscle cells. But that's only in 2D. And if we want to move towards more 3D systems, we need to be a bit more creative. In 3D, the most popular model to create skeletal muscle tissue probably consists in having muscle cells organize themselves between two posts, and when they mature, they will form fibers suspended between the two posts. Another way could be to create a hollow tube in a gel, and when you seed the cells in the tube, you basically mold muscle tissue in the shape of a tube. And with the advances of bioprinting, you can also directly bioprint an anisotropic cellular structure in a gel. However, there are still many limitations with all of these methods, especially because it can be quite hard to control cell organization, even more so when you're in a gel. So being able to remotely control cell organization can be quite practical. And from the title of my presentation, you might be able to see where I'm getting at, because in my case, I'm controlling cell organization using magnetic forces. And more specifically, I'm using superparamagnetic iron oxide nanoparticles. So these particles are superparamagnetic, and they're a few nanometers wide, which makes these particles are made of iron oxide and are a few nanometers wide, which makes them superparamagnetic, meaning that they are magnetic, so I can control them with magnets. But the moment I remove the magnet, there is no residual magnetism. So the force I apply is very precise. And in addition to that, these particles can be internalized by cells through endocytosis. And as you see here, this cell that was exposed to particles in its medium stores the particles in endosomes. And once the cells have internalized enough particles, they themselves become magnetic, which means that I can control them with magnet, just like these cells that get attracted to these magnets. And these cells in particular are the C2C12 myoblasts cells that I'm using and that I have labeled with magemite nanoparticles. And the reason why these cells get attracted by the magnet is of course because of the magnetic nanoparticles, but because of these particles, Each cell in the presence of a magnetic field becomes a magnetic dipole that gains a magnetic moment in the direction of the magnetic field lines. And thanks to this magnetic moment, a magnetic field can apply a force that is proportionate to both the magnetic moment and the gradient of the field. And thanks to this formula, we can even measure the amount of iron internalized through a method called magnetophoresis. And if you take this video, if I know the gradient of the magnetic field, I measure the velocity of the cells and their diameter, I can calculate their magnetic moment, and from that, I can also calculate the amount of iron internalized by the cells. And so first part of my work was to optimize this amount of iron internalized. So we tried different concentration of iron, and we also tried different duration. And we saw that we can have cells internalize up to 10 picograms of iron per cell with a single incubation, if you look at the curves in blue. But if we look at the metabolic activity in the curves in red, we can see that after these 10 picograms of iron, there seems to be an impact on the metabolic activity of the cells. So in order to increase further the amount of iron internalized without any impact on the cells, we thought that instead of doing a single strong incubation, we could do several consecutive weaker incubations. And in our case, we opted for 2 millimolar of iron for 30 minutes incubations, once a day over 3 consecutive days. And when we do that, we can have cells internalize 21 picograms of iron, and there is no impact on the metabolic activity of the cells, which is great for a magnetic tissue engineering application, and also seems to indicate that the incubation rate has much more impact on the metabolic activity of the cells than the overall amount of iron internalized. And so now that our cells are magnetic, we can start to mix them in our collagen matrix, which is still liquid at 4 degrees Celsius, and we keep it at that temperature for as long as possible to keep the collagen from polymerizing too soon. We pour this mixture in a PDMS well, and then we put our sample between 2 strong magnets. And now we can switch the temperature to 37 degrees. And because the cells are between the magnets, they will start to align in the direction of the magnetic field lines. But at the same time, because we're at 37 degrees Celsius, the collagen polymerizes, trapping the cells in an anisotropic configuration. And this is what it looks like in our samples. You can see the cells going from randomly dispersed to aligning in the direction of the magnetic field lines. And you might be wondering, well, why are the cells aligning in this case, when previously, when I put them next to a magnet, they get attracted to it? Well, the reason is that in this configuration, where the 2 magnets are facing one another, with the right distance, you can optimize the magnetic field so that it's pretty much uniform in between the magnets, meaning that its gradient will also be very close to 0. And if you remember, the force that the magnets can apply on the cells is proportionate to the gradient. So if the gradient is close to 0, the force the magnets will have on the cells will also be close to 0. However, even if this force is equal to 0, each cell still has a magnetic moment because it's in the magnetic field, and this magnetic moment is in the direction of the magnetic field lines. And thanks to this magnetic moment, each cell can actually apply forces on the surrounding cells. So it's actually the dipole-dipole interactions that create this alignment. And we can even control this alignment, and more specifically, the length of the chains we create. First of all, if we look at different labelings from 7 picograms to 21 picograms of iron, we can see that the more magnetic the cells, the longer the chains we create. We can also play with the cell density, and the higher the cell density, the longer the chains we create. And as you can see, these cell chains go from a few tenths of microns to several hundred microns, and under optimal conditions, they can even reach 1 millimeter. And now that the cells are aligned in a specific direction, we switch to differentiation medium, hoping that the cells in the same chains will fuse together to form fibers. However, that's not the case, because instead of fusing together, the cells actually start colonizing the gel, and in a matter of days, we lose the anisotropy. And we tried very different conditions. We even tried keeping the samples between the magnets all the time. but we still lose the anisotropy over a few days. So we needed to find a solution to preserve the anisotropy much better, and the idea we had was that instead of aligning individual cells, we could align much bigger objects, spheroids, and basically use these spheroids as biological building blocks that can be assembled magnetically. And because our cells are magnetic, we thought that we could take advantage of that to make our spheroids. So we designed an array of nickel and iron magnetic patterns that were made with photolithography and electrodeposition. And each magnetic pattern is basically a 100 micron wide magnetic dot. And if you put magnetic cells on top of these patterns, they will form an aggregate on each dot, and each aggregate will turn into a cohesive spheroid after only 3 hours. And because we can create a lot of patterns on a very small surface, we can create several thousand spheroids in only 3 hours very easily. And not only that, but we can even control the size of the spheroids we create. First of all, the more magnetic the cells, the bigger the spheroids. Well, more precisely, if the cells are not magnetic enough, they will not all get attracted by a pattern. But with our optimal labeling, all of the cells get attracted by a pattern. And if you know that, and you know the total number of patterns, you can easily calculate the average number of cells per pattern. And of course, the more cells you put, the bigger the spheroids will be in the end. For example, with 35 cells per pattern, you get a spheroid that's about 50 micron wide, but with 140 cells per pattern, you get a spheroid that's on average 100 micron wide. And now that we have our building blocks, it's time to see if we can align them. And it works just the same way it did with individual cells. We can create spheroid chains in a 3D collagen matrix. And same as before, the more magnetic the spheroids, the longer the chains, and the denser the spheroid density, the longer the chains as well. But here, not only can we control the length of the chains, but we can also control their width, because we can choose the size of the original building blocks we're aligning, which allows us to create a much wider diversity of anisotropic structure in our gel. And now it's time to switch to differentiation medium again, and the big question is, will the anisotropy be preserved this time? And the answer is yes, because if we look at a spheroid chain over a week, we can see at day 0 that the spheroids are in 3D aligned, nicely distinct from one another. At day 1, they've not colonized the gel much, but they fuse together to form a cellular fiber in the direction of the magnetic field lines. And at day 4, we can no longer see the original shape of the spheroids. And at day 7, when we look at the actin filaments and the nuclei disposition, we can see that they are all aligned in the direction of the magnetic field lines, and we can even see some fusion events occur. However, even though the alignment is preserved over time, we see that our fibers tend to compact a little bit. There's a loss of elongation, mainly because muscle cells are very contractile. And so to counteract this contraction effect, we decided to apply an opposing force by stretching. And so we designed a stretching system on which we can clamp our chips, and when we stretch our chip, we also stretch the tissue we create. And when we stretch it, our tissue stays much more elongated, and the cells as well stay much more elongated. And so with this magnetic alignment method, on which we have recently published a paper, in case you want to know more about it, we're able to create a large 3D collagen tissue in which we can have a wide variety of anisotropic cellular structures. However, there is still a very strong random factor in the alignment procedure we have. So as you saw, all the spheroid chains we create are very different from one another, and so are the cellular fibers we create, which makes it very difficult to study a single fiber at a time. Plus, when we looked at myoblast fusion, even though there were some events, it was not as optimal as we expected. So more recently, in a work in progress, we have started to explore a new approach based on magnetic stretching, which would allow us to study a single fiber at a time, a fiber that is reproducible, and in which we could improve fusion, all of that to study the impact of stretching on myogenesis. And this idea of magnetic stretching was previously investigated in embryonic stem cells that were labeled also with magnetic nanoparticles. And as these cells could be aggregated between two magnetic microtips, and they could be compacted or stretched. And cyclical stretching would induce cardiac differentiation in these cells. And so our idea was that we could adapt the system to skeletal muscle tissue. But if you remember, skeletal tissue is very anisotropic. And in this case, you have more of a cubic shape for your tissue. So we thought that instead of letting the cells just aggregate between two magnetic tips, we can pre-organize the tissue so that it already has an anisotropic shape. And we have just the tool to pre-organize the tissue, magnetic patterns. And if you remember the magnetic dots to create the spheroids, we're able to use the same technology to create magnetic patterns of any shape we want. And the shape we chose was the wrench, because it has an elongated central fiber in the middle, and it also has two clumps that are ideal to attach to magnetic tips. And from this idea of a shape, we made this magnet, and with this magnetic pattern, we're able to create this tissue only composed of aggregated muscle cells, and this tissue is very cohesive. It can easily be picked up and moved onto a chip. And the way we create the tissue works quite similarly to the way we created the spheroids. First, you create the pattern, any shape you want. Then you put the magnetic cells on top of it. They will aggregate, and in 3 hours, you get a cohesive tissue in the exact same shape of the pattern, meaning that you can create a tissue with any shape you want. We can control the shape of the clamps. We can control their length. We can also control the width. So we have a really good control over the 2D aspect of the tissue. But we also want to have control over the 3D aspect because we want to create 3D muscle tissue. And to do that, we can use the cell density, because as you would expect, the cell density per square millimeter of pattern also controls the final aspect of the tissue. And as expected, the more cells you put, the bigger the tissue will be. And we looked in particular at the section of the central fiber of the tissue. We looked at its height and its width, and we saw that both the width and the height stay proportionate to one another, no matter the cell density, but they're also both proportionate to the cubic root of the cell density. So by controlling the cell density, we also control the thickness of the tissue we create, which gives us a bit of control over its 3D aspect. And now that we have our tissue and our way to design it as we wish, we can also create our chip. We opted for our chip for EcoFlex material because it's biocompatible and elastic, and in our case, we used EcoFlex that is also transparent. And in this chip, you can see 8 compartments in parallel that are identical, and in each compartment, you have 2 nickel-plated iron needles facing one another. And our idea was that with the tissue, and when we magnetize the needles, because the needles on their own are not magnetic, we could easily get the tissue to be trapped between the 2 needles. And the idea was that we optimized the shape of the tissue so that it would attach as best as possible between the 2 needles. And that's our idea in theory. And let's look at what happens in practice. First, let's look at what happens when I don't magnetize my needles. I can approach the tissue with a pipette. You can see it here. It's a bit darker because it's loaded with magnetic nanoparticles. And because there's no magnets, the tissue doesn't get attracted by the needles. It just floats around. But now, let's see what happens when the tissue gets attracted by the needles, when we put magnets. I can approach the tissue just as same as before with a pipette, and you will see that the tissue will get attracted to the needle. It clamps onto the first needle with its first clamp, and when you move the pipette, it clamps onto the second needle. So we really have here a clip-on magnetic tissue. And thanks to the optimization of the shape, we're able to do this process very easily. And I can trap 8 tissues, 1 in each compartment of the chip, in only a couple of minutes. So we have a pretty good throughput. And then we just let the tissue adhere to the needles for a few hours to overnight, and then we can start stretching. And to stretch the tissue, we adapted our stretching system so that we can clamp a new chip onto it. And by stretching the chip, we increase the distance between the two needles, which will also which will also deform the tissue. And this is what it looks like when we stretch the tissue at twice its original length. We're able to stretch it that much without the tissue breaking in the middle or detaching from the needles. And now that we have this whole stretching system designed, we can start exploring the impact of stretching on muscle maturation. First, let's look at a tissue that was not trapped, not stretched, that was just left freestanding in an non-adherent well. We can see in this 3D reconstruction of confocal images with the actin in red and the nuclei in blue that in this condition, the tissue just evolves towards a more spherical shape, mainly due to cell contraction and surface tension forces. And in its internal structure, there's no anisotropy, no fusion. Now let's see what happens when we trap the tissue between two needles, but we don't stretch it. We just let it evolve on its own tension. And we can already see in the middle of the tissue that there is anisotropy of the cells. There is also some fusion events, and in some of the fibers fused, we can even see striation of the actin, which is a strong sign of muscle differentiation. And now, let's see what happens when we stretch the tissue at twice its original length. We can see that when we stretch that much, the tissue completely reorganizes itself and turns into a very elongated cellular fiber that is only 50 micron wide, but spans over several millimeters from needle to needle. And the tissue is not only very anisotropic at its whole scale, but also when we look at the actin and the nuclei. And especially, we looked at the actin orientation distribution for these three conditions, and we can clearly see that when we stretch the tissue, we create the most anisotropic structure. And so with our two approaches to create muscle on chip, whether it's magnetic alignment or magnetic stretching, we have shown that magnetic tissue engineering is a very useful and versatile tool to create microphysiological systems, whether it's to create spheroids, to pattern a tissue, to control cellular organization, or even the organization of bigger objects, to trap tissues or even to stretch them. There are a lot of possibilities. And in our case, it has allowed us to study the impact of anisotropy and stretching on muscle maturation. And there are, of course, a lot of things we still want to do with magnetic stretching, especially to optimize muscle maturation. And we want to know when and how to stretch to optimize maturation. For example, recently we started stretching for 24 hours and then releasing the tension. And when we do that, we do create some fibers, but they're just not in the right direction. They're at 45 degrees compared to the whole tissue, which shows that there's still a lot of things we need to understand better in muscle maturation and the impact of stretching. We also want to try cyclical and step-by-step stretching. I don't know if you can see behind me, but we also want to try more physiologically relevant cell lines. And finally, we also want to measure more precisely the stress within the tissue, which should highlight some very, very interesting mechanical mechanisms in muscle maturation. And I hope that we will be able to tell you all about this quite soon, so stay tuned. And of course, I want to thank all of the great people from my team, and especially my two amazing supervisors, Claire Wilhelm and Stéphanie Descroix, as well as in particular Simon Dumas and Giacomo Glopero, and all of the people involved in this project. And of course, thank you all for your attention, and if you have any questions, I'll be happy to answer them.
Thanks, Noam. That was really cool. Any questions from the audience?
Thanks for the presentation, really fascinating approach. I assume there's, how can you electrically, stimulate the structures, or will that be a...
That will be something that we want to implement. So far we're only studying the impact of mechanical stretching, but it's true that we could add electrical stimulation, either directly through the needles that the tissues are attached to, or maybe with an additional electrode. That's also a possibility. We're still exploring that, but we really want to study first mechanical stretching, and then see how we can complement that with electrical stimulation.
Would there be some sort of a risk of some sort
That
of...
would be interesting. That would be really interesting to see either if we do it with a synchronicity or asynchronicity. That would be interesting to see if that changes some things.
Cool. Thanks.
Any other question?
So, hi.
Hi.
Nice presentation. I love your approach. I'd like to see if you test any toxicity caused by iron in the cells or a change in physiology. Did you test these kind of things?
Yeah, we did test because it's, of course, we're introducing nanoparticles in the cell, so there's, of course, a risk of toxicity. That's also why we tested, first of all, for the metabolic activity. And as I said, we saw that when the incubation rate is too high, that it could have an impact on the cells. But as we saw, it's more the incubation rate than the particles themselves that have an impact, at least at the levels that we use. Because when we can have much higher levels of iron when we do consecutive labelings, and there's not as much impact than when we do just a strong incubation, a single strong incubation. And we also tested metabolic activity. We tested also with live dead. There's no problem. And we also looked at the morphology of the cells after labeling them, and whether we label them or not, we see the same evolution of the cells over time. So they still fuse the same way they did before. We even see, in some cases, we even see myofibers labeled with magnetic nanoparticles that even beat in 2D spontaneously. So the function seems to be preserved even with the magnetic nanoparticles. And it's also important to have in mind that these particles are degraded over time. So in the time we're using the cells, so a couple of days, the cells stay magnetic, but over a couple of weeks, it has been shown by Claude Wilhelm and Aurore van der Waal in our team that the particles get degraded. So it seems to be quite biocompatible, but of course, it's also only at the levels that we're using, but at least at this level, we don't see toxicity. Yes?
Thank you. I also liked your talk. Following that question, do you think it might change the mechanics of the cells and maybe impact their differentiation that you are trying to obtain in vitro?
What do you mean by the mechanics? You mean
the stiffness?
The stiffness
of viscoelasticity?
That is possible, but it's possible that it changes a little bit the stiffness because you have these endosomes that are filled with magnetic nanoparticles. So it's something that would be really interesting to test. We haven't done that yet, but so far from what we've observed, there's not that much difference between spheroids that are made with our method and spheroids that were made just by aggregation in a well, which is a more classic method. So for now, we don't think there's that much difference, but it's something that would be really interesting to test, especially since studying the mechanical properties of our tissue is also one of our goals to understand better muscle maturation.
Thank you.
Any other questions? Okay, maybe I have a quick question.
Yeah.
So I guess your goal in the end is to use it in vivo to create muscles or to help people who lose muscles. Do you have any thoughts on how you plan to do this?
Well, I think because there are two approaches, there are two ways you could see that. First of all, like this idea of the collagen tissue we create with the anisotropic cellular structure. Well, this collagen tissue, you can see that as we do it on a 1 centimeter by 1 centimeter cube. So you could see pretty much any shape of a collagen patch that could then be grafted. And the collagen patch can be as large as the space between the magnets, which is a couple of centimeters. So you could really have like I would say 5 by 5 collagen patch that you could then graft onto patients. And for the fiber between two needles approach, you have in each compartment you have fibers, so you could imagine just grafting fiber by fiber your tissue. So it's two ways you could see how to do grafts with this system. And of course, to jump back to the toxicity question, because the cells will degrade the iron over time, you will still get a tissue that in the end should have lose its magnetic properties, which is not something you necessarily want to have magnetic tissue in your body in the end.
Really nice. Thanks a lot. So I think in the interest of time, we continue. Thank you very much,
Thank
Noam, for the
you
wonderful
everyone for your
presentation.
attention.